We can predict whether a function's inverse will also be a function by applying something called the horizontal line test. So for a function, to test to see if something is a function, we have something known as the vertical line test. So if we think back to the graph in the previous video, we had a line that had a slope of 4 going across our graph. And so that obviously passes the vertical line test, but it also passes the horizontal line test. I can never hit the graph twice with the same horizontal line. And so as a result, that tells us that the inverse will also be a function. And that's indeed what we found. We ended up with a diagonal line that had a slope of 1/4 as our inverse. And so we can see that that passes the vertical line test. So the horizontal line test for the original function predicts that the inverse will pass the vertical line test, meaning that the inverse of the function will be also a function. In the second example from the previous video, we had a graph that looked like this as our original function. Again, it passes the horizontal line test, so then we could predict that the inverse will pass the vertical line test, and indeed it did. We ended up with a graph that looks something like this for our inverse. So for a graph that, let's say, was a parabola shape, this would be an example of a graph that fails the horizontal line test. We can hit the graph twice with the same horizontal line. And so what that tells us is that the inverse of that function, if we were to flip-flop all the x and y coordinates and plot them, we would end up with something that isn't a function. And so we would end up with a sideways parabola as our inverse. And so quite obviously, this sideways parabola fails the vertical line test. So the horizontal line test applied to the original is a way for us to predict whether or not the inverse will be a function and pass the vertical line test. So for circumstances where our original graph is going to fail the horizontal line test, we have to have a workaround. So we're going to cheat a little bit. And what we're going to do is we're going to basically eliminate half of our original function so that our original function will pass the horizontal line test, which then means our inverse function will pass the vertical line test. So if we take this first one here, so if we want to graph x squared minus 4, hopefully we recognize that as being a parabola with a vertex at -4. So I'm going to go down here to -4, I'm going to make a dot, and then we can use our regular pattern of left and right 1, up 1 from the vertex, left and right 2, and up 4 from the vertex, left and right 3, and up 9 from the vertex. And so here we have our original graph. And so quite clearly, this graph fails the horizontal line test. If I draw a horizontal line right here, I'm clearly hitting the graph more than once, which means my inverse is also not going to be a function. So what I need to do is I need to reduce the scope of the graph that I'm looking at. I need to basically eliminate half of this graph so that my original graph will pass the horizontal line test, and so then my inverse will also be a function. So this is how we can make a function be invertible. We restrict the domain of the original function. And so in most cases, we're going to restrict the domain to being just x is greater than or equal to 0, meaning I'm only going to consider the right-hand side of my graph. So I'm just going to pretend like this part isn't here. You could either erase it or just kind of X it out like I have here. And so now I'm going to flip-flop the x and y coordinates of the remaining part of the parabola that I see. So the vertex, if you'll recall here, was at 0, -4. So if I flip-flop those x and y coordinates, I can have a point at -4, 0. This point right here is at 1, -3. So I'm going to go to -3, 1. This point here is at 2, 0, so flip-flop that and we get 0, 2. And then the last point that we'll make use of is this one here at 3, 5. So I'm going to go over 5, up 3. And so there is the reflection across our line. If we want to add that in here, y equals x, there's the reflection of that blue line. So the yellow, or the red line is indeed the inverse. It's now a function because we eliminated half of that original function. So this is how we can render an original function invertible is by restricting the domain of the original so that the inverse will also be a function. Now we do want to find the equation of this function, so let's go ahead and write this as y equals x squared minus 4. So I'll flip-flop my x and y, so I get x equals y squared minus 4. So I'm going to start off by adding 4 to both sides. So I get x plus 4 equals y squared. And so now I'm ready to take the square root of both sides. And so if we recall, normally when we take the square root of both sides, we should put a plus or minus in front of our answer. So we get plus or minus x plus 4. But here's the problem, is we would end up with 2 y coordinates for every x coordinate. And so that would mean that we would not have a function. So by restricting the domain like we did here, that basically eliminates the plus or minus in front here. So we're only going to take the positive outputs, just like we only considered the positive x coordinates on our original graph. That means we're only considering the positive y coordinates on our inverse graph. And so our inverse function is just the positive square root of x plus 4. So there's our inverse of this restricted domain original function. Sometimes it's the domain of the inverse that needs to be restricted to have it match up with the original function. And so here we see an example of that. So we've got our original function here is this f of x equals the square root of x plus 4. So if we graph that original function, we've had experience graphing square root functions before. So instead of starting at the origin, because of the plus 4 that's here, we're going to translate the graph to the left 4 units. And so then from there we go over 1, up 1, continuing the pattern that we know, over 4, up 2, over 9 from that starting point, so 5, 3 is going to be that location. So here's our original graph. So if we wanted to flip-flop the x and y coordinates to generate the inverse graph, and of course we'll end up with a graph that's reflected across that line y equals x. So my first point here was at negative 4, 0. I'm going to go down to 0, negative 4. This point here was at negative 3, 1. So I go 1, negative 3. We've got a point here at 0, 2. So that's going to be at 2, 0. And if we wanted to go one more, we had a point here at 5, 3. So we're going to have a point at 3 and up 5. So here's our inverse graph. So far so good. But when we go to try to find this inverse function, if we jump over here to do that, again, starting with y equals the square root of x plus 4. So now I flip-flop my x and y. I get x equals the square root of y plus 4. So now I'm going to square both sides in order to get rid of that square root as I try to solve for y. So we have now x squared equals y plus 4. So for my last step, if I subtract 4, I get y equals x squared minus 4. Or if we want to use the inverse function notation, the inverse of f of x equals x squared minus 4. But we know that the graph of x squared minus 4 should be a full parabola, not the half parabola that we see on the graph here, having just generated the graph from flip-flopping the x and y coordinates. So what this requires of us is to make sure that we express that we're restricting the domain of the inverse. And so what are the x values of this inverse graph here? Well, we're starting from x equals 0 right here on the y-axis, and then it's everything to the right. So we're going to have a domain restriction of x is greater than or equal to 0 as part of our reported answer here. And so this is to make sure that it matches up with the fact that it's supposed to be the inverse of this original function, which is the square root of x plus 4, which is half of a sideways parabola laying on its side. So we just have to be conscious of that when we're finding an inverse function. Sometimes we have to restrict the domain of that inverse function to make sure that it is indeed truly the inverse of the original function we were given.